So the motivation for this topic comes from the intuitive understanding that code quality itself is something very integral to all types of activities that we do in software development lifecycle. Whether it's requirements, let's say we are writing clearer and concise requirements because we want our code to be more functionally relevant to the user expectations, or we're designing better tests, plans and test cases because we want to have less and less bugs in our code. And let's say also when we're designing architecture, we want our code to be structured so that it's more maintainable and we can add new functionality with ease as the software evolves. So the motivation I wanted to mention is sort of very much built in to the overall software development lifecycle. And a quote that is usually associated with Peter Drucker, he mentions that you cannot improve what you cannot measure. So measurement then plays a very integral role at code quality as well. And since the 70s, several studies have proposed source code metrics which measure some aspect of code, such as its size or its complexity or how structured it is. And several other studies, secondary studies, have reported how these code attributes can be linked to or are related to observable quality attributes such as maintainability of code or reliability of code. So our topic or thesis is basically divided into two goals or two studies. The first one is regarding the measurement aspect, and the second is regarding the improvement of code quality. And I'll just go briefly over the first one first. So the first goal is to classify source code metrics and report the link between source code metrics and external quality attributes such as maintainability and so on. And the first paper in this series explored the current state of the literature in terms of internal quality attributes, source code metrics, and how they have been linked with external quality attributes and external metrics. And for this, we performed a tertiary study, which included 15 secondary studies, and it reported the individual source code metrics that have been shown to have a link with maintainability and reliability and security. So the main question in a diagrammatic form was, what is the link between, or the reported link between source code metrics and external attributes such as maintainabilities? And for this, we performed a search in 3 different databases, and from 711 odd studies, we narrowed it down to 52 secondary studies that reported source code metrics, and then from there on, 15 secondary studies that reported a link between source code metrics and quality attributes. The nature of this link within these 15 secondary studies was of different nature. So it was associative, where they explored how source code metrics are correlated with external attributes, and it was also explanatory or predictive, where they used source code metrics as the independent variable to predict something regarding maintainability of source code or reliability of source code and so on. And we classified or we based our strength of evidence on 4 factors, them being the number of secondary studies that reported that evidence, the quality of those secondary studies reporting the evidence, number of primary studies within the secondary studies, and then the validation status of the reported metrics. So on a broader level, if a link is reported by large number of secondary studies and a large number of high quality secondary studies, and it also has a large number of primary studies reporting that link, we will say that that's a strong evidence that this link actually exists in the reported literature. The strength of evidence based on these 4 factors was classified into high degree of evidence, moderate, low, and very low. And one of our important results is now shown on the slide. So here we had maintainability as the external attribute. So the overall, the evidence reported largely related to maintainability and reliability. And then on, let's say, if we focus on one particular row, so complexity attribute, which is measured by response for class source code metric, was reported by 2 secondary studies with a relationship indicator of positive from 26 primary studies, and we evaluated it as a high degree of strength of evidence. And similarly, there are other interesting aspects here. So, for example, complexity, coupling, and size have at least 1 or 2 source code metrics which have reported a high degree of evidence for reliability. Similarly, complexity and coupling metrics, for example, RFC, responsive class, and coupling between objects, they also reported a high degree of evidence for maintainability. Sorry, just another addition or comment on this. This paper was finalized in June, and we submitted in IST. And at the moment, it's a submitted paper, and we're hoping to hear from the reviewers. Moving on, the next paper we had in our first goal included the research question that we wanted to classify source code metrics that have been reported in the secondary studies, and we wanted to present a catalog of these source code metrics for the use of practitioners and researchers. And one of the contribution was that we reported 423 source code metrics from 52 studies as part of that catalog. Going back to the same research results that we had in the first study that we also used for the first paper, from the 711 search results, we had 52 secondary studies that mentioned source code metrics, and we classified them using what type of internal attribute they're measuring. And then further on, we also further classified them at the scope at which they measure the source code metric and the unit of code that they use to measure the source code metric. An example of scope and unit of code can be seen here on the slide, where number of methods is a source code metric which measures size as an internal attribute, and its definition is count of all methods defined in a class. So here the method is the unit of code that is being measured by the metric, and class is the scope at which this measurement is made, which is, let's say, slightly different from another source code metric which measures at package level. So the scope can be different, but they are using the same unit of code. The catalog contained 423 source code metrics, which can be classified into by the internal attributes. So we had a larger reflection here was that despite the research over the last few decades, the attributes of interest are still cohesion, coupling, and complexity. And in our set of results, coupling actually had the most source code metrics related to the most source code metrics related were with coupling, with 161 roughly source code metrics that related to coupling. And when we classified the same source code metrics for scope-wise, we identified that at class level, most of the source code metrics actually measure the scope at which they measure is at the class level. With, you could see in the third row, almost 102 source code metrics measure coupling at class level, and so on. Sorry. This paper is also, we recently submitted the catalog as well as the paper earlier this month in Software Quality Days, and the catalog is available online for practitioners to view. So that's another minor contribution in this. Moving on from the overall first study. The second study focuses on the improvement part of code quality, and here we are interested in seeing how we can improve code quality by identifying issues discussed in review comments. And for this partial fulfillment of this goal, we're interested in how we can automatically classify code-related issues in review comments. And this is a study that's ongoing, and I will just be sharing a background for this and the proposed methodology that we will be using. So several studies have, it's sort of an accepted, I won't say fact, but it's sort of accepted knowledge that code reviews, when conducted in a development lifecycle, they improve code quality. And researchers have manually categorized what kind of issues they find in those review comments. So there are taxonomies that have been published where they identify what type of issues they find in code reviews or defects that they find in code reviews. And recently, there have been many studies that have classified those kind of issues. The approaches they have used can be varied. So for example, one approach is that they manually train their data set and then they apply automation for the later part of the test set. One limitation there is that whenever you have to train it, you have to basically train it for a new data set. If you're working on a new repository, then you have to again do the manual classification and then go for the automation of that data set. Our approach aims to limit that manual classification, or every time you have a new data set, and it uses a semi-supervised machine learning or topic modeling approach. And the automatic classification of review comments is our hypothesis is that it aims to help developers regarding which issues they have in their code base. And that could then help them with this feedback, and then help them resolve those issues and work towards other things that are more important in their development process. Just a small overview of our approach. So on the left side, we have the training stage where we're using an existing taxonomy of topics that have been identified in review comments. And we use those topics to manually label a data set, which has a set of words or a bag of words associated with each topic. And once we have this manually labeled data set, we move on to the inference stage where we train a review comments through an topic modeling algorithm. And then we come up with a new data set of inferred topics. At the moment, we have not labeled them, but we still have some topics within our repository with certain other bag of words associated with them. Then we do a cosine similarity between these bag of words that we found in the inferred stage and the ones we had already found in our labeled data set. If the cosine similarity crosses a certain threshold, we can say that, okay, this unlabeled topic was actually the same topic that we had in our pre-labeled data set. And through that approach, we are able to map the topic that we had identified in our training stage, and we can map it to an unlabeled topic in our inferred in our inference stage. Two decision parameters that I have to resolve here are what happens to the topics that don't reach a certain similarity threshold. So if there are new topics in the inference stage, they will naturally not meet any threshold when compared with the manually labeled set. So do I classify them as new topics, or do I exclude them from my considerations? That's one design choice that I have to make. And when I am at this matching stage, I can manually analyze them to see if they're relevant or not. And the other choice that I have to make is, do I update my bag of words if we have a new topic which uses certain other words as well? Do I update them in my manual data set or not? So those are the two things that I have to consider when designing this study. And once we have our new matched data set, then that could be used as a feedback loop to the developers that, okay, these are the topics that are of interest to the reviewers in your repository. It could be used as a feedback to update their programming styles, or let's say if they have certain naming conventions that they're not following, they can update that based on that feedback. Certain future works that I would like to carry out after completing the study is applying the automatic classification to an industrial data set to see if it can be generalized to other data sets. An industrial survey to gauge the effectiveness of the classification model, and a bug prediction model that I want to use, which uses process and product metrics to assist the reviewers to sort of help them where to look for potential bugs during a code review. So those are still something that's down the line. And I think I'm done. Any questions, comments?